Good day, everyone. So, today we'll be looking at a new topic titled Models of Atoms. Models of Atoms. In other words, we'll be looking at the ideas of different scientists about the structure of atoms. All right, so without wasting much of our time, let's dive into this topic. Okay, let's look at the first model. Now, the first scientist that talk about the model of atom, or the structure of atom rather, is Thomson. Thomson was the first person to describe the structure of an atom. And in his own description, he says atom is a homogeneous sphere that has positive charge inside. That has a positive charge, and then inside the positive charge there is negative charge particles called electrons, as you can see it here. So you see it as an homogeneous sphere, positively charged, but inside this sphere we have some particles known as electrons. As you can see, the minus sign there represents the electrons, and the sphere itself is positively charged. That is own description of an atom. It went further to say that the ratio of the charge of this atom and the mass of this atom are identical, irrespective of the type of atom that it may be. So that was his own definition or description of atom. That atom is an homogeneous sphere that is positively charged, and inside this sphere we have a negatively charged electron embedded in it. Okay, and that the ratio of the electron mass, the ratio of the charge and the mass of the atom are identical in all kind of substance. Okay, so that is Thomson model of atom. Now, after his own description of atom, another scientist came out to describe his own. The name of the scientist is known as Rutherford. Rutherford model of atom is kind of similar to that of Thomson. But what is different here is that he says in its own atom that an atom consists of a positively charged core, unlike that of Thomson that said it's an homogeneous sphere. In his own case, he says it's a positively charged core, and he called that core a nucleus. And that most of the mass of this atom are concentrated on this nucleus. He also said that this nucleus has an electron that is around it in form of an orbit. Okay, you can see it here. These electrons represented with the minus sign are what Rutherford said are around the nucleus of an atom. Okay, as if you have the planets surrounding the sun. So that's how he described his own. Thomson didn't relate the availability of an electron around the nucleus as the orbit or as the planet being around the sun, but Rutherford related this, that the electrons around the nucleus are just like the planet being around the sun. And he went further to say that each of the nucleus of the atom must be in a way that the electrons and the nucleus and the electron and the nucleus must be in a way that they must make the atom to be neutral. The atom must not be neutral. So in other words, if we have the nucleus having two charges, then the electrons too must have two charges, so that there will be what? Neutrality. So this is Rutherford's model of atom. And then Rutherford went further to say that atoms are not stable because these electrons here as you're seeing them, is according to its assumption that gradually the electrons will be falling down. Let us see its limitation. Look at this. In its limitation, he proposed that the electrons are not stable, that they keep emitting light, and gradually as they are emitting light, they fall into the nucleus. And that is the limitation of his own model, because another scientist later found out that what he said was not true. Rutherford discovery was proven wrong, that there is nothing like electron losing its energy and then falling into the nucleus, nothing like that, and that atoms are actually stable. If atoms are not stable, there is no way that we can have matters around us to be stable, because all atoms actually are what made up all atoms are what made up matters. Okay, so these two assumption of Rutherford that electron lose light and gradually fall into the nucleus have been proven wrong, and that atoms are not stable have also been proven wrong. And the scientist that did prove him wrong was Bohr. Bohr's model proved Rutherford's models wrong. In his own experiment, he found out that atoms are actually stable and that there is no continuous emission of light, but rather just a line spectra. So, in his own definition or explanation of atom, he said that yes, what Rutherford found out, that atom has a nucleus, is true. Atom has electron that are surrounding the nucleus in form of an orbit, is true, but that this electron do not fall into the nucleus. Rather, they emit line spectra and fall into a lower energy state. Each of the orbit is known as energy states. Okay, so when an electron moves from one energy state to the other, as you could see these electrons moving around, there is emission of line spectra. Okay, and we use EU to represent the initial to represent the energy of the upper state, and then we use EI to represent the energy of the lower state. Now, when energy moves from upper state to the lower state, it loses energy, and the energy is calculated as this: HF, which is the energy, equals to EU, that is energy of the upper state, minus energy of the lower state. While the H represents the Planck constant, the F represents the frequency. The product of the Planck constant and the frequency now give us the energy. Okay, so the change in the upper state energy and lower state energy is what gives us the energy loss by the electron when they move from one orbit to the lower orbit. So this is how Bohr explained his own model. All right, now another model came up again. It's called the electron cloud model. In this model, it was stated that we also have nucleus as well. Nucleus that had a positively charged, but this time around the electrons are in form of wave particles around the nucleus, unlike that of Model and Rutherford and Thomson. In the electron cloud model, we say the electrons are in form of cloud around the nucleus. That's just the difference between the other model. He didn't describe the electron around the nucleus as a planet around the sun, but rather they are in form of cloud around the nucleus. Okay, having said all the models, now the model we now use today is called the atomic structure. All these models are brought together to form the atomic structure, and eventually we could now say that the atom, okay, is made up of a tiny but massive nucleus, okay, at the center. And this nucleus consists of both proton, which is represented by P here, and neutron. So the combination of proton and neutron is what we call the nucleus. Now the combination of their number, proton number and neutron number, is now called the nucleon number. So proton plus neutron make up the nucleus. And then around the nucleus, we now have the electrons moving around as if the planet is moving around the sun, okay, in form of a wave around an orbit. Okay, now we're going to be talking about the proton, the neutron, and the electron. Firstly, we have been able to see that proton and neutron are found in the nucleus. Now, by mass, the proton and the nucleus, the neutron has the same mass, atomic mass unit. So the proton has atomic mass unit of 1. The neutron has atomic mass unit of 1 as well. But the electron is the lightest among these particles. So it has 0, approximately it has no mass. So it's the lightest particle among the particles in an atom. So its mass is approximately 0. It's not as if it's 0, but it is approximately 0. So it has no mass. Now, the charge on the proton is positive. The charge on the neutron is 0. It has no charge. The neutron has no charge. The electron is negatively charged. We've already said that the proton and the neutron are found in the nucleus, while the electron is found in the orbit. Okay? Now, atom itself is represented with letter X. Now, the proton, the number of proton, we use Z to represent it. You can see this is how we represent atom symbolically. So we use X to represent the atom itself. Then the Z, which is subscript, represent the atomic number, or what we call the proton number. Okay, so the atomic number or proton number are the same. Then the A represents the mass number. The mass number is the sum of the proton number and the neutron number. That means neutron plus proton give us the mass number, which is represented with capital letter A. So this is the summary of the atom in our world today. I haven't studied all the models of atom. All right, there is something we also call isotopes. Isotopes are just atoms that have the same element, but they have this different. The atom that have the same element, they have the same atomic number, but their mass number is different. Okay, for example, now hydrogen. Hydrogen has 3 isotopes. It has hydrogen, it has deuterium, and it has tritium. Okay, for the first isotope, it has only 1 proton, as you could see here, and 1 electron. But the second isotope, which is deuterium, it has 1 proton, 1 neutron, and 1 electron. And the third isotope, it has 2 neutron, 1 proton, and then 1 electron. Okay, so we say that isotopes are atoms of the same element that has the same atomic number but different mass number. Atomic number is the same thing as proton number. You could see here that this hydrogen, it has proton but only 1p here. For deuterium 2, it has only 1p. For tritium, it has only 1p as well, because they are isotope. But they have different mass number. Mass number is the sum of proton and neutron. Here now, the mass number here is just 1 for hydrogen. For deuterium, the mass number is 2. That is p plus n. 1p plus 1n, that's 2. While the tritium, the mass number is 3. The n plus p, that's 3. Alright, so this makes them to be what? To be isotopes. Another example is the chlorine. Chlorine, you could see this first chlorine. It has 17 protons, 17 electrons, and 18 neutrons. So in this case now, the sum of the proton and the neutrons is 35. You can see here that the mass number is 35. For the next chlorine, the mass number is 37. The atomic number remains 17. Alright, so these are isotopes. Once the atomic numbers are the same and the mass numbers are different, they are known as isotopes. Okay? Okay. So we will not go beyond this for now. In our next class, we are going to learn more on this. So thank you for listening. Bye for now.